What's going on, smart people? Now, I actually already just recorded a video for today, but I just found out that it's Richard Feynman's birthday. So needless to say, that video is going out tomorrow, and today is all about Richard Feynman. More specifically, one of his favorite methods of integration, differentiation under the integral sign. So the way we're going to start this off is I'm going to take an integral that I found online that withstands all of the tests and procedures of usual integration methods like biparts and U substitution. And then we're going to throw differentiation under the integral sign at it, and we're going to come out with an answer. So the integral that we're going to be solving today is the integral from 0 to 1 of t cubed minus 1 over ln of t with respect to t. Now, right off the bat, you might notice that the thing that makes this integral so ugly is this factor of ln of t in the denominator. And whenever you just have one little thing where it'd be pretty nice if that wasn't there, that's when you might as well give differentiation under the integral sign a chance. And the way we're going to go about doing this is by parameterizing a part of this function and making it a function of something other than t. And then what we're going to do is we're going to take the derivative of that with respect to that other variable and see if that's something we can exploit in this actual integral. Let me make some context here. So let's say we take a look at some function t to the x, and we want to take the derivative of this function that depends on x with respect to x, of t to the x. Okay, well that's just going to equal t to the x still, it's just an exponential, times ln of t. Now if t here, we're pretending it's just a number, right? This could be e. And then if this was e, then it would just be the derivative of e to the x, so that would just be e to the x still, times ln of e, which would give us just e to the x. So that works. Cool. Now with this in mind, what we're going to do is we're going to define a new function as an integral. So we're going to define some function, g of x, that is equal to the integral of t to the x minus 1 over ln of t dt. So you can see, and we're going to have this going from 0 to 1. And if we integrate this, well, we're adding up all the things that depend on t. The only thing that's left over is something in terms of x. That makes it a function of x. Okay. Now what we're going to do is, well, first off, let's look at this case. Let's look at the case that we look at g of 3. So if we have g of 3, then what we get is that x becomes a 3, and we just get this integral here. So really, I'm just defining this in a bit more abstract and general way. What I want to find now is I want to find what g prime is, g prime of x. And now, since it's a function of x, this means that I'm taking the derivative of this with respect to x. Okay, so what we're going to do, if we haven't added up all the things that depend on t yet, that means when we take the total derivative with respect to x and put it inside the integral sign, it becomes a partial derivative. So I want to take the derivative of this. So it's going to be the partial derivative with respect to x of t to the x minus 1 over ln of t with respect to t. Okay, well we could split up this part here into two fractions, or into two parts, right? It could be t to the x over ln t minus 1 over ln t. And when we attack it with this derivative with respect to x, maybe it's best that I write it out. That's the same thing as the derivative of this, d dx, t to the x over ln t minus d dx of 1 over ln t dt. So I just split up this fraction, and what we see is that this part goes to 0, right? Because this doesn't depend on x at all. That goes to 0, and we just need to find out what the derivative with respect to this is. Well, we just solved that up here. So this part comes out to, that tells us that g prime is equal to the integral from 0 to 1. The derivative with respect to x of t to the x is t to the x ln t. So we get t to the x over ln t over ln t dt. The ln's cancel, and we just get that this is equal to the integral from 0 to 1 of t to the x dt. Okay, well this is just power rule. That's nothing that we don't know how to take care of. So that's just going to come out to t to the x plus 1 over x plus 1. And we're evaluating this from 0 to 1. And what that comes out to, well, remember that this 1 and this 0 is corresponding to these values of t. So that's just 1 to the x plus 1 over x plus 1 minus 0 to the x plus 1. But that's just 0, so I'm not going to need to write that. Not to mention, anything to the any power, or 1 to any power, is just going to give us 1. So that tells us that this is equal to x plus, is just 1 over x plus 1. And that is equal to g prime of x. Okay, now I'm going to erase some of this, and we're going to see how to connect this to the initial integral that we wanted to solve. So now we have an actual expression for g prime of x, and what we're going to do now is we're just going to work backwards. We're going to take the integral of this with respect to x. So that tells us that g of x is equal to the integral of, or I guess the antiderivative of 1 over x plus 1 with respect to x. This isn't a crazy integral. You should recognize this as just being ln of x plus 1. And we're doing an antiderivative here, so this is going to have a factor of c. Okay, cool. So this is saying that these two expressions are equivalent. This integral of this ugly thing here is coming out to this plus some factor of c. And we need to find out what the c is. And we can find out what the c is just by looking at this function here and noticing that if we put in g of 0, so if we let g of 0, what is that? So let's see what g of 0 is. Well, we get something to the 0th power, which is just going to be 1, so we get the integral from 0 to 1 of 0 times dt, which is 0. So we have an initial condition that we can use to fix this factor c here. So what we can do is we can plug in 0 for x here and solve for what c must be. So if g of 0 equals 0, then g of 0 is equal to ln of 1 plus c, that equals 0. Well, ln of 1 is just 0, which tells us that c equals 0. Okay, so that tells us that g of x is equal to ln of x plus 1. And the case that we were interested in here is the case where it's g of 3, right? Because that's the initial integral that we wanted to solve. Because if x is 3, then we get this instead of this general expression here. So that tells us that g of 3 is just this evaluated at 3, which is just going to be ln of 4. Great. So once it's all said and done, that tells us that this integral that we were struggling to solve at first is equal to ln of 4. Thanks, Feynman! Now, what made me make this video was two reasons. One is that someone in the comment section reminded me that this is Feynman's birthday, and someone also commented that an integration technique that they would like to see is differentiation under the integral sign. So thanks to you two for putting this idea in my head in the first place. Hope you guys found this method interesting or a little bit helpful. Let me know in the comment section if you did, and I'll see you guys there.